critical number of like points that you need to have to put it small, or a point, and there's some point where it becomes
too small? Yeah. Suppose that you have 5 right-hand side variables and you only have 14 observations. Well, then I'd say you're in trouble. No, that's like the question when you took introductory statistics. One of the questions that came up was, how large is large? Right? Because your statistics instructor said things like, for large samples, the critical value in a t-table is the same as the critical value in a normal table. And somebody in class always says, well, how large is large? And the teacher says, well, look at the t-table at the back of the book. How many rows are included in the t-table after 30 observations? And you see, well, there are none. No table includes rows with more degrees of freedom than 30, because beyond 30 degrees of freedom, the critical values differ only in the third decimal place. And at that point, who cares? So in the olden days, people used to say, oh, 30 is a big number. These days, particularly in finance, 30 is a very small number. You can get to collect financial data every minute of the day now, for day after day after day. So tens of thousands of observations become big. So it depends on what you're doing. But you're right. You have to pay attention to the degrees of freedom problem. So this was this Goldfeld Quandt test was kind of the gold standard for many years. And you still see it in use now. Okay.
Why taking the root make the correct problem of how that diagram just for measurement purposes?
What's the square root of 2 times the square root of 2? It's 2. So suppose that the way the computer constructs a beta hat is as x prime x inverse x prime y, right? Suppose that's our regression model, and suppose that the expected value of u transpose is 2, 3, 4, all the way down to 10. Like that, okay? And so you want to construct a new estimator to account for this, right? And the way you want to construct your estimator in as computationally easy a way as you can. So what you would like to have for omega inverse is to have 2, 3, 4 all the way through 10, the inverses of those rather, a half, a third, a quarter, a tenth, all the way down, right? So you want to have to create as small a computational burden as possible. You want to figure out a clever way to get omega inverse in there. Well, a clever way to do it is to take the square root of omega inverse and multiply x by the square root of omega inverse, right? So what's the square root of omega? Square root of 2, square root of 3, square root, so on and so forth. So if I multiply that times x, then when I multiply x by itself, out pops omega inverse. And programmatically, that's a much easier job than computing. If you have 1,000 observations, can you imagine constructing a matrix with 1,000 by 1,000? You'd quickly use up even your gigabytes of memory on your motherboard. So instead, we found a cleverer way to do it. Just multiply element-wise the right-hand side variables by the inverses of, say, whatever you thought was driving the heteroscedastic